Hello again, YouTube. In this video we're going to continue our exploration of the irrational roots test when solving polynomials. Okay, so let's go ahead and get started with f of x here. You'll notice that we have a third degree polynomial that is entirely unfactorable, or at least unfactorable with any method that I know of. So that's been the rationale for using our rational roots test in the first place. Okay, so let's go ahead and start by generating our list of potential rational zeros that could go into this, because you'll notice we have integer coefficients, and the stipulation for using the rational roots test says that, hey, you have to have integer coefficients. So making our list of, let me get rid of this set notation here. Our list of potential rational zeros, we say it's all of the, factors of the constant term over all of the factors of the leading coefficient. So we say factors of 12. Now I'm using this example for a couple of reasons. First one is this 12 is a very composite number, okay? It's very, very, very not prime. But it has several factors. So we say plus or minus 1, 2, 3, 4, 6, and 12 are its factors, and 12 plus or minus 12. And then on the bottom we say factors of the leading coefficient, which are tens. We say plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Now, in previous videos, if you've been following these, you'll notice that I tend to write these things out in roster notation, or an entire set notation of what these could be. So potential rational zeros at this point are 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. And then we move on. We say, okay, so how about 1 over 2, which is a half, 2 over 2, which is, by the way, the same as 1, which we've already listed, 3 over 2, 4 over 2, which is the same as 2, which we had already listed previously, 6 over 2, which is 3, which is something we've already listed. Bottom line is we could list out all the potential rational zeros of this, but it is convenient. It is convenient to leave it in this form and know how to read this or navigate this with your eyes. Okay, so let's say we did not have a graphing calculator. At this point, since we had something that was not factorable, we at least know this. Since it had integer coefficients, then its potential rational zeros must be on this list. Furthermore, we could sit here and just synthetically divide out any of these values from the original one until we found one that went into it evenly. However, we do have a graphing calculator, and I think that if you have a graphing calculator, you should be using one. However, also, I would start by testing 1 into this first, okay? I mean, if I didn't have a graphing calculator, that's what I would go with first. We say, how about negative 10, 15, we'll graph it here in a second. Don't worry, I'm not going to make you sit through a bunch of stuff here. We say, we could check 1 first to see if it goes in. So does 1 go in? Well, the mystery is now solved. Check it out. 1 does not work. If you look at this graph with me, actually you'll notice this. It has 3 zeros. This was a third degree polynomial. So we know that according to the fundamental theorem of algebra, it has to have exactly 3 complex roots. And at most 3 real roots, but if not 3 real ones, it could also have just 1 real root. Obviously, it crosses the x-axis thrice, and so we have 3 real roots. Oops, I didn't want to do that. So 3 real roots. Bottom line though is this: if you're looking at this on that list, you see one between 0 and 1. This could potentially be a rational zero. It could potentially be irrational. Bottom line though is, it's kind of hard to tell. Negative 1. I don't know if you can see this. It kind of looks like it's close to it. On a graphing calculator, honestly, you might not be able to tell that negative 1 is, I'm going to be honest with you, not a rational zero on this function. I'm using this function on purpose. But 2 most certainly is. So, looking at this picture, we're going to go with the closest one. We're going to divide out the one we're very, very comfortable with. First is 2. So let's say we put our 2 up here. We'll go ahead and get started. We say, okay, so negative 10 times 2 is negative 20, plus 15 is negative 5, times 2 is negative 10, plus 16 is 6. Times 2 is 12, and hey, you know what? We were pretty sure we were going to get no remainder anyways, or a function value of 0 at the x value of 2. So good news, cool beans. We've actually got a 0. One of our zeros is 2, and that was rational. That was on our list, 2 over 1. So we want to find the other 2, so we'll write this out now. We say, okay, so negative 10x squared minus 5x plus 6 is the remaining expression, and we could probably factor this, and I know that this is not everybody's favorite, but we have an a value that is not 1, so we're going to have to do a little bit of guess and check. So setting this equal to 0, we say, okay, so factors of negative 10, that's interesting. Can you do this? Well, I'll tell you what, when you want to factor a trinomial with a leading coefficient 1 or not 1, you tend to want that leading coefficient to be positive. So our method here is going to be this. We could, and I know what you're thinking, we could just multiply everything, both sides of this equation by negative 1. But we don't actually want to do that, because if you think about this, I mean, if you were to graph, say, this remaining quadratic here, since it's even degree, it's end behavior, it starts and ends the same way, and since it has a negative leading coefficient, this would be like a parabola that opens down on its own. If you were to divide out the -1, all of a sudden you'd have a parabola that opens up. It may have the same zeros, but it opens up. We don't want to change the orientation of this. Our method is going to be this. We're going to factor that negative out front, and we get 10x squared plus 5x minus 6 is 0. Again, we just did this so that we can split this expression up, and we'll just put that negative. We'll just throw it right out here in front. Negative. Now we don't have to worry about it. So we say, okay, so if we're going to do a trinomial with an a value not 1, we need to line ourselves up with getting a 10x squared in front first with our FOIL. We want to do our f part of our FOIL first. And so we say factors of 10 include 1 and 10, and also we have 5 and 2. I'll give you a little hint. You should usually start with the closest of the two factors. We say 5x and 2x. Now we're guaranteed to get our 10x squared. Now we need to get a -6 back here. So we could say, well, maybe it's -3 plus 2. And you know, I've already got a good indication that this is probably not going to work because I have 2x plus 2 over here on the right. And if that's the case, I could factor a 2 out of both of those. And if that was the case, I would have been able to factor that out of the beginning expression in the first place. We'll go and check our outer and our inner here. So we say, well, 5x times 2 is 10x, and then -3 times 2x is -6x, and a positive 10x, a -6x, that simply doesn't add up to 5x. So we could try again here. We could flip around our -3 and +2. We could say, how about -2, +3, and check our outer and our inner. And so, you know, we say, okay, well, you know, 5x times 3 is 15x, you know, minus is 4x, you get in the middle. That also doesn't work. So maybe it's the case that 2 and 3 just aren't our lucky numbers. We could go maybe 6 and 1, +1, -6, outer, inner. We get on the outside 5x, on the inside -12x. That also doesn't sum to -5. So that's not working for us. So maybe we switch our 6 and our 1 around. We say, okay, so -1 plus 6. We say, okay, the outer, we get 30x, and -2x is 28x. These are not working. Not working. So maybe the case was this. We simply needed to start with, instead of 5x and 2x, we'll start with 10x, and 1x. And we could say like, oops, sorry, got a phone call coming in there. We say -1 plus 6, outer, we get 60x minus 1x. That's not going to happen for us there. So maybe we switch our 6 and our 1 around. 6 and 1 gets switched around. -6 plus 1. So we say 10x and -6x. That doesn't work for us. And then last but not least, our last option would be maybe we need a -2, +3. So now we're getting +30x minus 2x. That doesn't work for us. And maybe -3 plus 2. So +20x and -3x. We keep not getting this 5 in the middle. What does this mean, ladies and gentlemen? What this means is this. This is certainly just a non-factorable trinomial. But I wanted to do this example on purpose, not because you know, not because I wanted to make you think, but because of this. I typically tend to give my students these two hints when we you know, factor polynomials. First of all, you should always check for a common monomial factor first. And in this case, you know, our polynomial, it didn't have something that all of those terms had in common. But the second thing is this. If you're ever left with like a second degree thing, whether you want to or not, the quadratic formula is always an option, always an option. Okay, so we say quadratic formula in this instance, we say x is equal to -b plus or minus square root of b squared minus 4ac all over 2a. Okay, and looking at all of this together, I'm going to tell you what, I want to point this little quantity out more than anything here. We're going to give it a name. This is referred to on the inside of there as the discriminant. Not discriminate, discriminant. Okay, and the reason why I want to look at the discriminant is well, two reasons, honestly. We already know by looking at our picture that we're going to get 3 real zeros here. So what that means to me is this. When we do our quadratic formula, whatever was inside this radical, I'll tell you what, must have been positive. Okay. Furthermore, if what we get underneath the discriminant or underneath the radical, or you know, if the discriminant is negative, we're going to get 2 complex roots because we're going to have imaginary stuff. What if the discriminant is actually equal to 0? What if the inside stuff here is equal to 0? Well, I'll tell you what, if that were the case, you'd have an expression that said plus or minus 0 over 2a, but the radical 0 is just 0. You would have this. Basically, -b plus 0 is -b. and negative b minus 0 is negative b. So you'd get a repeated 0 if the discriminant were ever 0. So let's go ahead and find b squared minus 4ac first, since we need to know it. Just saying. It's a good habit. So we say in this case, looking up here at our trinomial, we have a is negative 10, b is negative 5, c is 6. So we say b squared would be negative 5 squared. Let me switch colors. Negative 5 squared. A was negative 10, and then c was 6. So going ahead and evaluating this, we get 25. Negative 4 and a positive 10 that's 40, and 40 times 6. We say plus. Okay, so plus 240, we get 265. So when we do quadratic formula now, we're going to say x equals negative b plus or minus radical 265 all over to a, where a was negative 10 and b was negative 5, negative 5. So we get positive 5 plus or minus radical 265 over negative 20. I'm going to write this out. We say, okay, so our two roots must be this: 5 plus radical 265 over negative 20, and then 5 minus radical 265 over negative 20. And I think it'd be worth our time to actually convert these to decimals just to show you what's going on here. So let me see if I can't get this to work for me a little bit easy here. 5 plus radical 265. So let's do this. We say, we could use this guy over here. 265 radical, whoops, let's clear that. Radical 265, enter. Please and thank you. Maybe it wants an end parenthesis, I'm not sure. There we go, they want me to buy their calculator. Radical 265, so we get this, we say, well, let's just write it out. 5 minus radical 265. Thanks for being patient, everybody. 5 minus radical 265 equals, divided by negative 20, so we'll say 20, and that's negative, so really we'll take that times negative 1. So we get 0.5639-ish, so 0.564. So we're going to go back over here. We say this is approximately 0.564. Don't lose that. And then this one over here is 5 plus radical 265 divided by 20, negative 20. So, whoops, 5 plus radical 265. All of that, enter. Sorry about that. Divided by negative 20. Then we get negative 1.064-ish. Okay, so negative 1.064-ish. So negative 1.064-ish. Okay, so these things that I've got vortices around, there was 1, 0, 2, and then we got these other two zeros. Negative 1.064 and positive 0.564. I just want you to see this. Positive 0.564 is not, unreasonable, and negative 1.064 is entirely reasonable. So the fact of the matter is this: we used the rational roots test, and we got 2 to work because it was a rational 0, and the other 2 zeros, well, they were real, all right. It's just that they happened to be irrational. They involved radicals. So just know that you can always use the quadratic formula if you have a quadratic thing left over, 2 zeros left to find.